In this video, we will be going over the 9-point circle, also known as Feuerbach circle, Euler circle, and Turcom circle. This is presented by Tammy Tran and Lisbeth Martinez for Math 3321 at the University of Texas at Dallas. Let's dive in. The theorem states that given a triangle ABC, if we draw the three altitudes and label the feet, label the three midpoints, and label the three Euler points, all points fall on one common circle. This circle is present in every triangle. We'll get into the proof shortly. Feel free to skip ahead to the proof while we establish the foundation of our understanding.
Going into some background, you may be wondering why there's so many names. It was once thought that Euler was the earliest discoverer of the 9-point circle. However, this attribution was a mistake, as no one has been able to prove it. So, who is the discoverer of the 9-point circle? According to historical research by J.S. Mackay, the discovery of the 9-point circle has been attributed to several independent researchers of English, French, German, and Swiss origins. One of the notable discoverers is Feuerbach, a German mathematician that lived a short but significant life. He is accredited to the first published proofs relating to the 9-point circle in 1822. Turcom, a French mathematician, officially designated the term 9-point circle and published a proof where the 9-point circle touches the incircle and net circles. Back to our proofs, we will first go over a few key concepts. First, we'll define the points of the circle. An altitude is a perpendicular line through a vertex to the opposite side. If we draw the three altitudes of a triangle, we see that these lines meet at one concurrent point. We call this point the orthocenter. The midpoint, as you may guess, is the middle of 2 points in a line segment. An Euler point is defined as the midpoints of the segment joining the orthocenter to the vertices.
We can prove that the intersection of altitudes is always concurrent for any arbitrary triangle. Given triangle ABC with altitudes AP, BQ, and CR, we will show that they meet at one point. Through each vertex, we will draw a line parallel to its opposite side, forming triangle XYZ. We see that the points Z, A, C, and B form a parallelogram. You may already know this, but a parallelogram is defined as a quadrilateral in which both pairs of opposite sides are parallel. In another video, we can show that this also implies opposite sides are equal. Using this understanding, we show that ZA is equal to BC. Similarly, looking at parallelogram AYCB, we see AY is equal to BC. Hence, ZA is equal to AY. Now, we know that AP is perpendicular to BC since it is an altitude. We also know that our line ZY is parallel to BC. Thus, AP is perpendicular to ZY. We can state that AP is a perpendicular bisector of line ZY. A perpendicular bisector is defined as a line that bisects another line at a right angle through the midpoint. Likewise, using similar steps, we can state that BQ is a perpendicular bisector of ZX, and CR is a perpendicular bisector of XY. Therefore, using the understanding that perpendicular bisectors are concurrent at the circumcenter, we have proven that altitudes AP, BQ, and CR are concurrent. We will now take a brief look at similar triangles. Two triangles are similar if the three angles of one triangle are equal to the three corresponding angles of the other. For triangles to be similar, they must fit into one of the following criteria. Side angle side criteria, where sides appear in ratio, side, side, side criteria, where sides also appear in ratio, or angle, side, angle criteria, which can be shortened to angle, angle criteria. This is because if two angles are equal, then the third corresponding angle must also be equal. We denote triangles are similar with this symbol and read it as triangle ABC is similar to triangle EFD. Take note that we should list the points in corresponding order of equality.
Next, we will take a look at the basic proportionality theorem, which states that if a line is drawn parallel to one side of a triangle intersecting the other two sides in distinct points, then the two other sides are divided in the same ratio. Since DE is parallel to BC, then AD over AB equals AE over AC equals DE over BC. Now we will take a close look at the midpoint theorem, which states that if we draw a line segment connecting two midpoints, then that line is parallel to the third side of the triangle. The line joining the midpoints also equals half the length of the third side of the triangle. In triangle ABC, let D and E be the midpoints of AB and AC respectively. Then AD over AB equals AE over AC equals 1/2 because of the basic proportionality theorem. Angle DAE equals angle BAC since it is the common angle. By SAS criteria, triangle ADE is similar to triangle ABC. Therefore, AD over AB equals AE over AC equals DE over BC equals 1/2 because of the basic proportionality theorem and similarity of triangles. Because of similarity of triangles, angle D equals angle B and angle E equals angle C. Thus, DE is parallel to BC. Now we will give a short overview of the inscribed angle theorem, which states that an inscribed angle lies on the circle. It is always equal in degrees to 1/2 the measure of its intercepted arc where its endpoints intersect. If AC is a diameter and B subtends arc AC, then angle ABC is a right angle. Using our understanding thus far, we would like to prove that given any triangle ABC, the 3 feet of the altitude's 3 midpoints and 3 Euler points all lie on a common circle. We denote the concurrent point of the altitudes as H, the orthocenter.
Drawing diameter YQ and considering its unique circle, we want to show that midpoints P and R lie on the circle. For P, we will start by drawing line PQ. Using the midpoint theorem, since we know that point P and point Q are midpoints of sides BC and AC respectively, and AB is the third side, line PQ is parallel to AB. Similarly, if we draw line YP, in which P is the midpoint of line BC and Y is the midpoint of line BH, and CH is the third side, line YP is parallel to line CH. Since YP is parallel to CH, it is also parallel to CF. Since we know PQ is parallel to AB and CF is perpendicular to AB, YP is perpendicular to PQ. Thus, angle YPQ is a right angle. Since the endpoints of YPQ are the endpoints of diameter YQ, we have shown that point P lies on the circle with diameter YQ. We follow a similar process to show point R lies on the same circle. Drawing line YR, since R is the midpoint of AB and Y is the midpoint of BH, YR is parallel to AH, thus AD. Likewise, we draw line QR, since R is the midpoint of AB and Q is the midpoint of AC, QR is parallel to BC. Since RY is parallel to AD and RQ is parallel to BC, and AD is perpendicular to BC, RY is perpendicular to RQ. Thus, angle QRY is a right angle. Since the endpoints of QRY are the endpoints of diameter YQ, we have shown that point R lies on the circle with diameter YQ. So far, we have shown points P, Q, R, and Y lie on the same circle in which YQ is the diameter. We use a similar process to show that if XP is a diameter, points R and Q fall in the circle, and if ZR is the diameter, points P and Q fall in the circle. Next, we have angle YEQ is 90 degrees, since PE is an altitude. So point E is an inscribed angle that lies on the circle with diameter YQ. Likewise for points D and F. Thus, we have proven all 9 points lie on the common circle. We will now apply our understanding to a slightly more difficult proof, the 9-point circle on an obtuse triangle.
The 9-point circle can be reduced to an 8-point circle. In an obtuse isosceles triangle, the foot of the altitude and the midpoint of the base points K and L are in the same place. All the other points, D, E, F, G, J, M, and N, remain the same as in the 9-point circle. 8 is not the limit though. This number can be further reduced. The 9-point circle can be reduced to a 6-point circle. In an equilateral triangle, each side midpoint ends up at the same place as an altitude foot. J equals D, F equals M, and K equals R. The other three are the midpoints of the segments connecting the orthocenter to each vertex, points X, Y, and Z. Also, the orthocenter H is equal to the center of the 9-point circle, Q.
Furthermore, a 9-point circle can be reduced to a 5-point circle. In a scalene right triangle, the 5 points included in the circle are the midpoint of each side, M equals Y, X equals J, and K. The vertex of the right angle A equals Z equals C, and the foot of the altitude to the hypotenuse R. However, 5 is not the minimum. Incredibly, a 9-point circle can be reduced to a 4-point circle. In an isosceles right triangle, the 4 points included in a circle are the midpoints of each side, M equals Y, X equals J, and K. The vertex of the right angle, A equals Z equals D, and the foot of the altitude to the hypotenuse, R. A quick observation is that the foot of the altitude to the hypotenuse moves to the midpoint of the hypotenuse, meaning that K equals R. This reduces the number of distinct 9-point circle points to its absolute minimum 4. Do you think you can find a circle with 7 points or with less than 4 points? We challenge you to try and let us know in the comments below what you come up with. Thanks for watching.
We would like to give special thanks to Dr. Akbar.